So a little bit later, J.J. Thomson, 1800s, 1900s, he constructed a cathode ray tube. We have a diagram and a photograph here of a cathode ray tube. This was a partially evacuated chamber, a glass tube, and a high voltage is applied across the electrodes at each end. And what happens is there's a ray that travels from one end to the other. It's called a cathode ray. So we get a beam, it's a beam of particles, and those particles travel from the negative electrode, which is the cathode, to the positive electrode, the anode. So in our diagram here, we have voltage here, it's a high voltage. We have a negative charge here and a positive charge there. And in order to complete the circuit, particles travel from the cathode to the anode through this partially evacuated tube. And if you look at it in operation, it looks like that. You can see this glowing ray in there. So that was called a cathode ray. So, that's like really cool and all. And then the question, of course, is why does it do that? What are those, what's causing it? How? Why? Right? So Thomson found that the particles in that ray had particular properties. They traveled in straight lines. They were independent of what the cathode was made out of. So that metal end, the electrode, could be any metal, and the cathode rays were the same. And those particles carried a negative electrical charge. So we have to have a concept of what electrical charge is. So that's what this little picture over here is. So you can have a positive electrical charge or a negative electrical charge. Electrical charge is not the same as a magnetic field, but it behaves in much the same way. We play with magnets, right? We don't play with electricity so much because it's a bit shocking, right? So with magnets, we know that magnets have two different ends, right? There's a north pole and a south pole. And if you put two north poles together, the magnets will pull together and stick to each other. And if you try to put two south poles or two north poles together, you can push, and depending on how strong the magnet is, you might be able to get them to touch, but as soon as you let go, they fly apart, right? So the positive and negative electrical charges are like the opposite poles of the magnets. If we have opposite poles, opposite charges, they will attract each other. If we have two positive charges, they'll repel each other like two north poles. Two negative charges repel each other like two south poles. If we have charges of the same magnitude and put them together, they essentially cancel themselves out. They add up to zero, and the thing that they are in together has no overall charge. So those are the basics of electrical charge. So electrical charge results in attractive and repulsive forces between the particles. So Thomson was able to measure the charge to mass ratio of those cathode ray particles using electric and magnetic fields to deflect that beam. The beam travels in a straight line, but you can apply electric and magnetic fields and cause the beam to bend. You bend it to the right, you can bend it to the left. So here he's doing it in an evacuated tube, and you can see where it hits at the end. So based on how far it deflected, based on the charges, etc., he was able to determine that the charge to mass ratio was minus 1.76 times 10 to the 8th coulombs per gram. Okay, that's not a number you need to remember, but there it is. Yeah.
I don't quite understand what the charge to mass ratio is.
Let me go back if it will let me. So the question is, I don't understand exactly what this charge to mass ratio is. So these particles have mass, but he wasn't able to determine what their size was, what their mass was. And he couldn't measure the individual charge, but he could measure the ratio of the charge to the mass. And he found that that ratio was the same for all of the particles. Yeah, good question. So this implied that those cathode ray particles were about 2,000 times lighter than hydrogen, the lightest known atom. So this was very disturbing because this implied that the indestructible atom could be chipped. You can break little pieces of an atom off. So this like flies in the face of the statement by Dalton that atoms are indestructible, right? Because apparently you can break pieces off of them. So, this is not a chemical history class or a history of chemistry class, and so fast forward, what he had discovered was the electron, a negatively charged particle inside the atom that has very low mass. And all atoms have electrons. That's why you can get these cathode rays, and they're always the same, doesn't matter what the material of the cathode is made out of. So this was the first evidence that all elements are formed from the same particles. American physicist Robert Millikan in 1909, was just after Dalton's atomic theory, performed what's called his oil drop experiment. And from this, he was able to deduce the charge of a single electron. Did you have a question? Not really. No, I don't think they really knew about the protons yet. The electron was the first particle to be discovered. So I'm going to show you a video about this, but I'm going to talk you through it first. And I'm not going to test you on Millikan's oil drop experiment, but I'd like you to try to get your mind around it because it's really kind of cool. So he's got this weird apparatus here. Here he's got like a perfume bottle with an atomizer. You squeeze it and it causes the perfume to spray out in a mist, right? Except he's got oil in here. And so he's using the atomizer to spray this really fine mist of oil. So that gets sprayed out here and is little tiny particles, and they're subject to gravity, so they fall down. He's got two plates on the inside of this, a positively charged plate on the top and a negatively charged plate on the bottom. So a lot of these particles just hit the surface of this plate and it ends up getting all oily up there. But there's a hole in the middle. And some of the particles just happen to fall through the hole in the floor. And as they fall through the hole, they're just going to continue down like particles do. But then we have this ionizing radiation beam that's going to hit them and give them a negative charge. Now they're charged particles. Charged particles will move in an electric field. So he can manipulate the charge on the positive and negative plate. They're negatively charged particles are going to be repelled by the negative charge down here. If the charge is great enough, you can get the particles to just be suspended in midair because of their charge. So he's got a light source in here and a viewing microscope so he can look at these little tiny oil drops. So let's see someone else's explanation of this.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates, As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
It's not really, the catchiest video. It's like a computer voice, right? But I couldn't find anything more fun than that. Now, that had a lot of equations in it, and some of you are going, don't worry about it. But some of you are headed into science, and you can recognize that this is really cool. Because how do you measure the mass of something that's way too small to see? Even today, scanning tunneling microscopy can give us fuzzy images of atoms, but we can't see electrons. How do you study stuff that you can't see? It's challenging, and the challenge can be fun. So let me go over this again. So the particles are falling through this hole. So as they fall with the microscope, he could measure how fast they were falling and figure out the mass of each of those oil particles. Okay, I didn't mention that part earlier. Then he zaps them and gives them a negative charge. So what we know now is that some of those oil drops might have gotten 1 electron, some might have 2, some might have 3 electrons. They have different charges, and they've got different masses as well. They can measure their masses by how fast they're falling. So then he applies the electric field and looks at a particular particle and gets it to stop moving. From that, he can figure out the charge on that one particle. So he's got the charge on the particle and the mass of the particle. So he can do the ratio and find the charge to mass ratio of these different droplets. Well, they had different ratios, but he looked at all these different ratios and found that all of these ratios were a multiple of the same number, and that was the electron. So that gave him the charge on the electron. And again, this is not a number we need to memorize, but the charge was minus 1.96 times 10 to the minus 19. That was the ratio, the multiple, and so that was the charge. The unit is coulombs. And from Thomson's mass to charge ratio with the cathode ray tube, he could figure out that the mass of an electron was 9.1 times 10 to the minus 28th grams. Again, mind-bogglingly small, because atoms are too small to think about. And electrons are like 2,000 times smaller than atoms. Any questions? I'm going through this experiment not because I'm going to test you on the details of it, but because I want to illustrate a process in science where there are a lot of things that we cannot measure directly. And so we measure indirect things, and by thinking about how those quantities are related, we can find out things like the mass of something that's too small to see.